All right, so welcome to part 2 of the M4 Structure Studio block. We're going to be starting with an overview of M4SS Sketch, and then Joe will lead us through a UAM demonstration of the tool. So, like I said, my name is Thomas Nishenzi. Last section, I went over the M4 Structure Studio Sketch Point layout tool, and then this section, I'm going to be going over the Sketch module. So first, I'll be giving an overview of how the M4SS Sketch fits into the larger Structure Studio workflow. Then I'll give an overview of what sketch models are and how they are defined by the user. Finally, I'll talk about the different component and analysis cards that can be added to a sketch model. And these cards will be what define various structures and load cases in the sketch model. So here we have, again, an image representing the Structure Studio process. First, we start with the OpenVSP model. Then in the sketch point layout tool, the user adds sketch points to the surface of the component. These sketch points are the common building blocks in Structure Studio, and they're used to define various structural and aerodynamic features, as well as define load cases. Third, we transition to M4SS Sketch, where cards are used to define all that model information, such as property regions or aerodynamic panels. And Sketch will be the primary focus of this talk now. And then finally, Structure Studio takes all the information defined in M4SS Sketch and uses it to automatically generate a NASTran-ready finite element model. So now onto sketch models. Here we have the Structure Studio UI. Right now we're looking at it with the sketch model view activated. Every part of the sketch model is defined with sketch cards. For example, to define a material, you would add a matte card, or to define a control surface, you might add a control sketch card. So on the left of the UI, you can see the sketch model tree, which contains all of the sketch cards. Beneath that is the properties editor. This is where you would define all the fields of the sketch card. Then taking up the majority of the UI, the model viewer. This provides a visual representation of all the sketch cards that have been added to the model. Something I'd like to point out again is that when the sketch model is finished, Structure Studio uses all those cards to automatically build a NASTran-ready BDF for the vehicle. Here, we're taking a closer look at the sketch model tree itself. At the top are merge cards. These cards define how Structure Studios should merge the component level finite element models together and the order that they should be merged in. Beneath that are where the analyses are defined. Sketch model can contain any number of analyses, and each analysis can have any number of subcases. This model, for example, shows three different analyses have been defined: a normal modes analysis, a design optimization, and an aeroelastic flutter analysis. Then within each of these analyses, additional sketch cards are added to define various parameters, loads, or constraints for the analysis. Underneath the analysis section, we have the components. These components were grabbed directly from the OpenVSP model. And then within each component, there's various subcategories of cards. Subcategories are aerodynamic elements, materials and properties, the modeling parameters, points, which will contain sketch points, and the structural elements. Then all of these cards sum up to make the complete component level model, and then together all these component level models make the complete vehicle and sketch model. So previous users of Structure Studio may have been a little put off by our old sketch model UI. So I'd like to go over some of the improvements we've made over the year. Cards can be added to the sketch model through context-sensitive pop-up menus. Similarly, cards can be removed by right-clicking on them and selecting delete. And finally, cards can be edited with the properties editor. Together, just these three functions are all you need to define a complete sketch model. And that sketch model would be ready to generate a Nastran-ready finite element model. Furthermore, the model tree is color-coded to help troubleshoot any problems with the sketch model. Within the tree, all sketch cards are highlighted in green, while branches that are simply for organizational purposes are not highlighted. Then the colored circles can be used to locate any potential problems with the sketch model. Any card marked red will tell you what is wrong and will need to be modified or deleted from the model. Cards that are marked yellow were recently added by the user and simply require a quick review by the user to verify that the fields were defined correctly. And then finally, when all the cards are marked green and every desired sketch card has been added, then the model is valid and can be used to generate the finite element model. So now I'm going to go over some of the more commonly used component cards. So here are some of the structural sketch cards that are used to define structural elements in Structure Studio. First, we have the skin card. These define the regions where outer surface plate elements should be added. In the bottom right image, you can see that the whole model has been paved with the blue skin 4 quadrilaterals, which translates to the fully defined outer surface fuselage shown in green. Beam and frame cards are used to define internal plate and bar elements. Beam elements are defined as a line between 2 points, which translates to a projection of plate elements through the model, and that's shown in an example of that shown in the upper right. Frame cards translate to bar elements for the model. They can be defined a number of ways, and that's shown in the bottom left. And then finally, you can add attachment and landing gear cards. Attachments can be used to rigidly attach non-structural discrete masses, such as stores or engines. The LDGR card, or the landing geared car, is a version of the attachment card that was designed specifically to model the extended landing gear of a vehicle. There are other structural cards, but these are just a few I wanted to highlight. Next, we have materials and properties cards. Material MTRL or material cards can be used to define isotropic or orthotropic materials. The prop or properties card utilizes material cards to define isotropic shell, laminate shell, or isotropic bar properties. On the right, we can see a composite layup defined by a prop card that contains different layers of various material cards. Finally, we have the prop tag card. This card does not actually affect the analysis in any way, but allows the user to group different property regions together for weight statement reporting. So, for example, you might want to know how much all the internal structures of the wing weigh. So you would group all those property regions together with a single prop tag. Then, when the weight statement is generated, you would then be able to view all the masses as a single mass. Next, we have aerodynamic cards. The Aero4 and Aeroparam cards are used to define vortex lattice elements and splines. These can be used in aerostructural analyses. Additionally, the user can define control surfaces with the control card. Currently, users define these cards just like any other card, but hopefully in the near future, we'll have the capability for directly utilizing control surface definitions from the OpenVSP model itself to create these cards automatically. So if you have a detailed OpenVSP model with several control surfaces, you would be able to directly import them into Structure Studio, which would hopefully save you a lot of time. Finally, I'm going to talk about some of the analysis cards that can be added to Structure Studio models or sketch models. Analyses are defined with analysis cards, and subcases are defined with case cards. each analysis has a Nastran solution tied to it. Currently, we support linear statics, normal modes, static aero elasticity, aeroelastic flutter, dynamic aeroelasticity, and design optimization solutions. We plan on adding a buckling solution type as well. Additionally, there are 22 unique cards available to define various analysis parameters, constraints, or loads. On the right, I've included an example set of analyses for a sketch model. This model contains 5 different analyses. Each has their own set of subcases. And basically, Structure Studio allows the user to quickly define any number of analyses for the model. So I'm going to go over a couple of the analysis cards available in Structure Studio. This is just some of the more common ones, or a select subset. The first card I'd like to talk about is the load card. Load card can define many load cases for various types of analyses, and it's as varied as can define loads as varied as a point force load to a flutter load. On the right, you can see how the surface pressure card was used to define loads acting on a region of elements. Below that, you can see how point force and point moment might be used to provide load cases for a rotorcraft. And here are just a couple of other analysis cards. The fuel card can be used to define fuel loads on the aircraft. Depending on the analysis, this can be defined as the distributed mass, force, or pressure on an enclosed surface region. Additionally, it automatically takes into account the volume of the fuel and utilizes the defined acceleration to see how the fuel itself pools within the tank. Slings are used to create case-specific non-structural weights. This allows the user to include different non-structural masses for different load cases while maintaining the same vehicle model. On the right, we can see the fuel card acting on different regions defined by the tank card. And then below that, we have an image demonstrating a slung with a 3D jump analysis. So to summarize, the sketch model is initialized from the sketch point layout model, which places sketch points on OpenVSP components. Sketch provides a simple card-based framework for creating Nastran-ready finite element models. And then these sketch models can contain both the component and analysis cards, where the component cards define structural and aerodynamic elements, and then the analysis cards are used to define Nastran solution types and various parameters within that load case. So there are 6 different types of solutions available, and then 22 different analysis cards can be added to them. And then multiple analyses can be added to any model. So that concludes my portion of the talk, and I think I'll be handing it over to Joe now, who will talk about a UAM demonstration of Structure Studio.
Thank you, Thomas. Joe, are you ready to share your screen?
Yep, I'm ready to go here.
Okay.
Okay.
All right. Are you ready to go?
Yep, let's do this. All right. Hello, everyone. I'm Joe Robinson from M4 Engineering. And so far, we've learned about what M4 Structure Studio is and how you make a model in it and how you bring that over from OpenVSP. And today, I'm going to go over sort of the how and sort of what that looks like. Yeah. And we're going to do that using this urban air mobility side-by-side helicopter demonstration, which is developed by NASA. And so we're going to start out here on the right with this OpenVSP model that came from NASA Ames. And what we're going to try and do is get a minimal structural weight, and we're going to have various load cases relevant to this kind of a configuration. So we've got here like a tandem side-by-side rotor, 6-passenger helicopter type configuration. So I'm going to break down a little bit of what's in this OpenVSP model and which pieces of it we're going to use in size. So in the dark blue boxes here, we see the components that we're going to create structural meshes for and that we want to size in an optimization. So that is the fuselage and the wing strut. We're also going to mesh some components, but leave them at their baseline values and not size them in the optimization. So that here we're doing the horizontal tail and the windshield, which is sort of that front portion of the fuselage there. And then we've got some other components that we're not going to model structures for, but we are going to include as non-structural masses. So the landing gear, the rotors, and the engines, and things like that. Okay, so one of the first choices to make when making a Structure Studio model is a material system and applying those to the different regions. So we've gone here with a carbon composite layup for the fuselage and the wing strut. And internally, we've got aluminum ring frames and beams. And we can see the windshield here in green. It's going to be a plexiglass type material, and we're not going to size that. For our material layup, we've gone sort of a standard carbon sandwich here with UD on the outside, and then alternating plane weave carbon plus minus 45 and 0.90, 3 plies each, and we've got a symmetric layup here. And then for our optimization, we're going to size those outer carbon UD layers to give us our optimized design here. In addition, we're also going to size the aluminum frames with the radius, so they're represented as rod elements. All right, so our non-structural masses, luckily here we have a lot of good sources for our non-structural masses, and we've broken them down into the groups here. All of these are using either the attachment or the landing gear card, which are point non-structural masses, and then we're going to rigidly attach those to various components. So you can see mostly the fuselage and the wing strut here. All right, that's it. Okay, so load cases here. We're looking at a couple of typical helicopter type load cases. We've got a 2G jump, which we're going to represent on the bottom left there with point loads at our rotor centers. And then we've got a 1.33G landing, and we're going to represent that with loads through our landing gear we defined. So on a configuration like this, the wing and the tail keeps moving, they don't have very large areas, and so we don't expect like a pull-up type maneuver to be very significant for the structure. If you're looking at something like a tilt rotor, that's definitely something to keep in mind. You can use both of these like helicopter type load cases and aero trim cases, like a pull-up or a pushover type maneuver. Okay, so now we're going to go through, we sort of defined what our model is going to be like, how we're going to pull it together, what load cases are significant, and now we're going to talk about how do we make that in M4 Structure Studio. So just a reminder here of the basic process. So we started at the sketch point layout, where we take in our OpenVSP model, and we're going to put points on it. And those points are going to represent our structural hard points, where we're going to attach masses, where we're going to define internal structures, those sorts of things. Then we do the majority of the work in our sketch module here. We're going to define those materials, those load cases that we talked about, and we're going to set up our analyses. Then FEM and merge are the automatic components. So we're going to mesh our geometry and then merge all the components together. And then finally, we'll run through Nastran to do the design optimization, and we'll post-process that and get a weight statement. Okay, so the first step on that process, the sketch point layout, we've got our 3 components here that we're making structural meshes for. So that's the fuselage, the wing strut, and the horizontal tail. And here we've laid out sketch points. So this step and the next step, you can kind of think of them in tandem, because you're going to want to place your points at the locations that have significance in the structure, and we'll see sort of how we've chosen those in the next slide. But most of the time, fuselages and wings, you want sort of a grid of vertical and horizontal lines, points that allows you to make your standard structures like ribs and spars and frames and bulkheads. Okay, so here at the sketch step, we've got all of our sketches laid out. So here, the wing strut and the horizontal tail are quite simple structures. We've got the blue rectangles here represent our skins. So these are going to be our upper and lower skin OMLs. Those will be represented with quadrilateral shell elements. And they're going to have the carbon composite materials. On both the horizontal tail and the wing strut here, we have an array of spars and ribs. So we've gone with a 2-spar design with evenly spaced ribs on each. It's a pretty standard setup. I think the most interesting one here is on the fuselage. So again, we've gone with the skins for the OML here, but we've got some more interesting internal structure. So at the very front, the red line, we've got a bulkhead. Where we have these red horizontal lines, we're going to get internal floors. So we've got a floor here for the cabin, and then we've got sort of a ceiling, which is going to be where some of our large masses are. We've got an engine and those kind of large mass items up there. And then where we have the orange double lines, we're going to have ring frames. So we're going to have a series of those that run through the fuselage here. Okay, so once we've defined that internal structural layout, we run through our automatic process here, and we get a mesh. So you can see on the left, we've got the OMLs of all of our components. In the center bottom here, we can see our internal structure. So we've got the beams and ribs of our wing strut there. We can see the bulkhead and the 2 floors that we made. And then you can see the rings in a little more detail in the top right here, the teal. So we've got rings that go around the OML of the fuselage, and then we have a couple of beams that cross through our floors there as well. All right, so let's go into some Nastran results here. So this is for our sized structure. And we're looking here at fringes of max and min principal strain, which is our criteria for a composite layup material. And we can see this 2G jump, which is where we're putting load through the rotor hubs vertically. We mostly get strain in our wing strut, which is what we expect. We can see the top and bottom there. We get peaks near the inboard sections. So the way we broke this up property material-wise is there's a series of materials span-wise out the wing strut, and those are sized independently. And so we see we get a couple of sections of high strain where those materials have sized down to the minimum to meet our allowable criteria, and then also give us the minimum weight. For this configuration, the landing, we don't see very high strains here, and so we don't get much of a sizing impact from this load case. Right, and finally here we've got the weight results. So we have some published estimates that we're comparing to here, and we see most places we're pretty close. We're a little bit lighter on the wing strut, about 17% lighter. Horizontal tail, remember we did not size in this example here. Probably we'd need some other kind of a load case to better size that, for example, an abrupt pitch maneuver or something like that. And then overall, we end up with quite a close result. As I mentioned, there are a few enhancements we could do to this kind of analysis. So if we add some more load cases, we could size that horizontal tail. And we're working currently on some different types of rotorcraft load cases, including crash scenarios, which are often critical for many structural elements. And then additionally, we're currently in work on integrating with some rotor-specific analysis tools, such as RCAS, where things like the whirl flutter for the rotors may become a critical load case. And so we may see a modification when that feature is implemented. Okay. And I'll go through some future work and conclusions based on this demonstration problem here. So as I mentioned, we have crashworthiness loads modeling in the works as part of our CTRPP effort for NASA. And we're also integrating some rotorcraft tools that will allow us to model and analyze rotor structures and analyze them in combination with fuselage structure. So we'll be able to combine the effects of rotor, fuselage interaction, that sort of thing. So we've given a workflow of M4 Structure Studio here today, and we've gone through a modeling approach for the UAM side-by-side rotorcraft. We've looked at some preliminary results for sizing, namely in the wing strut, and we showed pretty good agreement, but there are elements that we could improve with some more features which are in development. And yeah, I want to thank the NASA SBIR program and the CCRPP from Ames, Langley, and Army Ames, which helped fund this research. And that concludes the M4 Structure Studio section. So if you want to get in contact with any of the speakers here today, or M4 Engineering, you can look here.
All right, thanks, Joe. That's a really good demonstration, and it kind of shows how you can stretch your legs with M4 Structure Studio and get it integrated with Nastran and do some of this really interesting work. So I really appreciate you guys taking the time to demonstrate and talk about the software, and really great advancements leveraging the API and making it a standalone tool. So really congratulations on all that work.
Thanks, Brandon.